3.2 is measures of variation. And I forgot to type the learning objectives. The key concept is that variation is the single most important topic in descriptive statistics and inferential statistics, right? So you might think about that, right? How much a group varies is very important, right? And it is the more difficult to grasp your head around, right? So that's why they call it the most important, right? We're going to talk about, I think that's ready to finish, 3 important measures, right? And variance and standard deviation are like, how would I want to say? One of them's the square of the other one. So if you know how to find one, you can easily find the other one, right? So range and standard deviation, I'm sure if everyone heard the term standard deviation at least somewhere before, even if you're not entirely sure what it is. Okay, so our focus, right, we will talk about how to compute them, but again, your calculator, computer, technology can compute things, right? They're very good at that, but you need to be able to interpret and understand them, right? As people doing different businesses, you will have to perhaps look at statistics to decide to make decisions. Should you implement a new software, right? So that's more what we're going to focus on in this class as much as possible, especially on celebrations. There'll be some writing. Typically, unlike averages, you will always get, specifically because it involves taking a square root. If you've ever taken a square root of a non-square number, you notice that the decimal goes on forever without repeating, right? So the question is, what do you round? Round to one extra figure than your original data is in there, right? That's just the rule of thumb. Okay, range is easy. It is the difference between the maximum data value and the minimum data value. Is this outlier resistant? No, not even close, right? Because it literally is using the extreme of values and calculating it, right? So it's not resistant. However, that is kind of okay. Sorry, it's not great. All right. In the context of range, right? For center, you want your outliers to not affect your center, right? You don't want it to have a big fact. When you're talking about variation, your outliers do talk about how varied your data is, but you don't want to have it completely overdo it, right? Unfortunately, it's very not resistant, right? So you need something that is more descriptive, and it doesn't really take the whole set of data into account, right? In the same way the mid-range doesn't. So you need something that's less outlier resistant and takes the entire set of data into account, right? And that is called, it's the better measure that we need. And that measure is standard deviation. It is the standard measure of how much a set deviates. It does not have a simple one-sentence definition. It is calculated in a very specific, non-straightforward way. Right? And again, you could have the standard deviation of a sample, right, which you use letter S, and then this is also sigma, but this is the lowercase letter sigma for the standard deviation of a population. The two have slightly different formulas, right? Unlike the mean, right, it's much harder to calculate a population mean, but if you somehow had all the data from the population, you would calculate it in the exact same way. Not the same in this case, and we'll get to that probably mostly on Monday. this is the formula. I think that's gonna need some explanation, right? A little complicated looking. So we'll talk about that. One, this is a formula for the sample. We'll talk more about this. Standard deviation, again, tells you how much data values deviate away from the mean. That's why for each data value, you're subtracting the mean from it. That's part of that. The standard deviation is never negative. Why? Because a square number is always positive. It could be zero if it's zero, but it's never negative, and the square root is always of a positive number is always positive. Larger values of S indicate greater amount of variation, right? Because the more extreme values are, the more you're going to have differences, right? When you subtract the mean from it repeatedly and add them together. Now, the standard deviation can increase dramatically with several outliers. So it's not outlier resistant, but it's more outlier resistant than the ranges. But again, you don't want it to be, it's not, right? Being outlier resistant entirely isn't good because standard deviation is telling us, well, how much values are outliers? How much are we away from the middle? Right? You could imagine two populations, right? You could imagine this class having an average age around 19. You could also imagine a class that has older adults and secondary age people in it, right? Could also have an average age of around 19. Some sub-Saharan African countries, right? Think Malawi, Tanzania. They might have an average age of around a mean age of around 19. That's probably also the mean age of this class. There's a much greater standard deviation, right? Because you go to this country, there are a lot of young people, there are old people. Here, roughly everyone's the same age. That second group would have a larger standard deviation. The standard deviation, despite this complicated formula, and you can done this in the chemistry class or something, you can do dimensional analysis. You will notice that you're squaring something and taking the square root, they kind of cancel each other out, the original units, right? So just like if I measure everyone's height in here in feet, right, my mean will be measured in feet. The standard deviation is also in feet, right? Same units. This is complicated, but it's a bias. We're going to talk about this one. This is something that I just want to roughly mention, right? We mentioned about inferential statistics, but we're not quite there yet, right? So, when you are inferring the population mean, right? Your best guess for it is the mean of your sample. That is not true for standard deviation, right? The sample standard deviation is not the best guess for the population standard deviation. And that's why it's called a bias estimator. It's really hard. The book mentions this here. I'm just giving you a taste of this now, right? Because this is, at this point, we're not really done any inferential statistics. Something that's difficult to really get your head around, right? But I promise, if you don't understand this now, you will. I can't tell you will, but I will give you what you need to understand this later. All right, so this is the formula. It's not very easy to use, right? So let's think of this formula as a procedure. And we will do an example of this. So that bar, I don't know how it migrated up so high, but it's here, right? So notice You're calculating with each piece of data and the mean. So the first step is to find the sample mean, right? And you easily know how to do that, right? Add them up, divide by n. Next is to fill, there's other methods, but the method I'm going to teach uses this. So let's say you calculate, you find your standard, your mean is 5. And let's say you have the data pieces 7 and 4, right? Let's say you have some more though, right? So you subtract, so 7 minus 5 is 2. You square that, that gets you 4. 4 minus 5 though isn't 1, it's -1. You square that, you get 1, right? I will show a better example. So you do this for each piece of data until you fill all these columns. Then you take the third column, you add all these numbers together, you divide by n minus 1, finally you take that square root. And of course, being the number of pieces of data. That's a little overwhelming. One, don't worry. You're not going to actually do this that much because technology, right? So I'm going to do an example by hand. When you're doing the homework, don't do that many examples by hand. Do just as many that you know how to do it. See what I'm saying, right? So that when you have to do it by hand, the one time you will on an assessment, you'll be able to show up to do it, okay? Right? Don't spend a lot of time on it because you're going to see it's quite cumbersome. I know it doesn't make a ton of sense right now because you haven't seen a full example, but questions, you want to ask a question before seeing the example, you're ready to see it. Let's show it, okay? Again, remember this is all online, so you don't have to write down word for word. All right. We will do Dan by hand, and then we will do Barb with the calculator, right? Okay. Step number 1, right? And remember, this is our formula. So to be able to use this formula, one thing we need to know is X bar, which is the mean, right? So the first step is to calculate the mean. That's really easy. So I need to find X bar, which you just, of course, add these together. Divide by the number of values, which in this case is 6. I did this ahead of time, and when I did that, I got 74. This is 74% because it's a test score, right? Next part is to make the table that I mentioned. X is 55. Write this down for each data value. Let's practice this. So to find each value, you do the calculation here. So in this case, it would be X, which is 55, minus 74, the mean, which is negative 19. Then to get the second one, I'm not going to write this out each time. I'm just being really clear about how I'm doing it. (361) negative 19 times negative 19, because remember, of course, when you do it, the squares will always become positive. So let's just practice this. See if you can fill out the rest of the table on your own, right? Using your calculator and your paper, all right? I promise you won't have to do this too many times. All right, let's go through this. If you didn't quite finish, that's okay. So this, let's go through these. So what did we get here? This first value is, so this difference was, what else we have? We got 12, 22, and then, all right, and we get 26 and 12. Okay. So then all you have to do is square this, so you get 144, right? These will always be positive. Yeah, that is negative 12. The nice thing, it doesn't really matter that much, because notice what the final step is that you add up the squares. So it's actually okay not to pay much attention to whether it's positive or negative, right? Because then finally what you do is you sum the squares. In this case, that's 361 plus 144. I did this earlier and I got 2,650. So that is this part of the formula. Finally, you have to divide this by n minus 1. That minus 1 is mysterious. I always use by. I will teach you a little bit about it later, but just notice, remember, n is the number of numbers in your data set. We have 6 here. In this case, you divide by 5, so you end up looking for the square root of 530, which gives us 20 point. So remember, the rule is, right, even though it's a 0, I should round it. So I should show that it's 23.0, right? So that is my standard deviation. Notice it was quite cumbersome to calculate, even though it was only 6 numbers. Yes? Oh, absolutely not. Actually, if you type that in your calculator, it is close to 23. It's like 23.065. Something goes on forever, right? Because it comes from the square root, right? And remember, unless you're rooting a number that is actually a square number, it is always going to be disastrous. And remember, this is percent, because the standard deviation you also calculate the same way. So now let's learn how to do that on our calculator. The cool thing is you actually already know how to do this.